Welcome to Hot Chips 25. Session 3, SoC 2.
About to start the SoC2 session, what perhaps should be called the Power in SoCs session. We have two really great papers for you here. The first one is titled AMD's Richland Client APU SoC. The speaker is Praveen Dongara. Praveen is a system architect and principal member of technical staff at AMD, where he works on mainstream client A APUs. Praveen has 12 years of experience at AMD working in the areas of performance optimization, system architecture, and dynamic power and thermal management. He has a master's degree in computer engineering from Purdue.
Okay, good afternoon, everyone. My name is Praveen Dongara, and I worked on the Richland client APU over the past couple of years. So Richland is the AMD's third generation A-series APU. It's a mainstream APU, mainstream clients, as in mainstream notebook and mainstream desktop is where the APU is used. And it's a follow-on to the second generation APU, which was Trinity, which was released last year. And Richland, by the way, has been launched already. Okay, so one of the important areas where lots of significant enhancements have been made is the power management area on Richland. So most of my talk is going to be centered around that particular area. So this is the agenda I'm going to use. I have a single slide where I cover key features, single slider which lists all the key features. And then I'll dive into the power management area. To be more specific, I'll talk about the AMD Turbo Core technology, which is our boost algorithm or boost technology. So before diving into the exact specifics of this technology, I'm going to walk you through some of the basics, some of the building blocks towards how the technology works, what are the control loops which are in play, and where exactly the Richland enhancements have been made. And I'll be covering improvements to the battery life as well. And some of the other salient features on Richland are we have AMD wireless display, and also we have the dock port technology, which is analogous to Thunderbolt technology out there. And finally, I'll talk about the results, both performance and battery life. OK, so this is a single slider that captures all the key features on this particular APU. By the way, APU stands for Accelerated Processing Unit, which essentially means that we have the GPU and the CPU both integrated. We also have a bunch of multimedia accelerators integrated in the same die as well. And as I stated, this is the third generation APU. We had Llano to begin with, which was first generation. The second generation was Trinity. And then we have this particular APU here. So right off the boot, I would say improved performance and power efficiency. People are usually surprised to see the big numbers here. So we have up to 29% higher CPU performance over the previous generation APU. And we have up to 41% higher GPU performance as well. And I'll be showing you exact performance slides later in the presentation. And the way we achieve these particular amounts of performance is mainly due to the improvements on the AMD Turbo Core technology, as I've just mentioned, as well as we have higher frequencies. And the frequencies come about by tweaking the process node. We still use the 32-nanometer process, but we have made process tweaks to get higher frequencies given the same power budgets. So we also have higher memory speeds, especially on the high-end parts, high-end SKUs on Richland. The memory speeds have gone up by speed grade. So on notebook parts, we have up to 1866, DDR3 1866. And on desktop parts, we have up to DDR3 2133. And battery life improvements have also been made. Mainly, we optimized the voltage and frequency operating points, and also the process tweaks have helped with the battery life as well. And in general, compared to the previous generation product, we have about half an hour to 1 hour battery life improvements, depending on the workload scenario. We also have improvements made to the AMD Start Now technology, which essentially results in quicker S3 and S4 resume times. And we also have motherboard compatibility. So this is package compatibility with the previous generation product, Trinity. So that actually helps OEMs for quicker time to market and minimize development costs. They can essentially use the same motherboards that they have developed for Trinity and pretty much plug in our part. We have also added an additional feature called configurable TDP. So given a particular SKU, Richland SKU, you could have a rated TDP on that, but depending on the system cooling capabilities, if you want the part to operate like a lower TDP part or a higher TDP part, we can actually make that happen by a software switch. This is typically in the BIOS. And some of the additional features are wireless display and dock port technology, as I've just mentioned. We also have, unique to AMD, the AMD Radeon dual graphics technology, wherein we can have the integrated GPU in the APU, as well as a discrete GPU work simultaneously to get better performance on gaming workloads. And a special mention to the battery life improvement with respect to HD video playback. We have up to 51% improvement there. OK, so before diving into the AMD Turbo Core technology, this is our boost technology. I would like to cover some of the basics there. So what is the motivation for this technology? So in many workload scenarios, by the way, this is a simple graph where I'm showing APU power on the left-hand y-axis and the APU temperature on the right-hand y-axis. And there are many workload scenarios where the TDP budget is not fully utilized. And there is also temperature margin left if you do not have the AMD Turbo Core technology. So the idea is to not leave power and temperature headroom on the table. You can actually leverage that to get higher performance. OK, brief history on the AMD Turbo Core technology. It was introduced in 2010 on the AMD Phenom 2 processor. It was fairly simple at the time. We just looked at the number of cores that are active. And if half or more number of cores are inactive, the rest of the cores are actually placed in a higher boost state. It was as simple as that. But later on, with the first generation AMD A-series APU, we started calculating power on the die. We have the so-called system management unit where the firmware can actually calculate power real-time dynamically. And based on the calculated power, we can make boost decisions. But as far as power transfers, if GPU is idle, it can actually transfer the power budgets to CPU. In 2012, with the second generation AMD A-series APU, we used both calculated power as well as calculated temperature. There are unique advantages to do that. And then we also introduced the notion of bidirectional power transfers. So both power transfers can happen from both GPU to CPU as well as CPU to GPU, depending on who's idling. So 2013, this is where we are. So along with the power and calculated power and temperature, we also have a notion of censored the measured sensor temperature. So we can actually detect real temperature using sensors on the die, and based on which we can complement whatever we were doing previously with the calculated temperature and get higher performance, and have slides on that. And we also have efficiency of power usage as one of the boosting criteria, and I have more content on that as well. Okay, so more basics. So thermal entities is a fundamental concept in the AMD turbo core technology. Before I go there, let me briefly cover what Richland incorporates in terms of what's there on the die. So you have the 2 pile driver dual core x86 modules for a total of 4 cores. Each x86 module has 2 megabyte L2. And then you have the VLI W4 based graphics cores, and also lots of multimedia accelerators are also over here. So in terms of thermal entities, we have 3 thermal entities. The first one is first x86 module plus the L2. The second one is the second x86 module and the L2. And the third is the graphics, Northbridge here, and also the multimedia, all clubbed together. So what does a thermal entity mean? Thermal entity means that we can actually control frequency and voltage separately on each of these entities. We can actually track power and temperature separately on each of these entities as well. And I/O power, which covers the additional memory PHYs and display PHYs and PCI PHYs. So I/O power is tracked separately, and the influence of I/O power on the other thermal entities is accounted for. Okay, so first step towards building the control loop that you need for the boost algorithm. So first, you need to have a notion of calculated power. So for that, we have activity sensors throughout the die. And in terms of each of the thermal entities, you can have activity monitored over a certain period of time, and you get a notion of AC capacitance, or CAC. And as most of you know, simple equation for the dynamic power, CV squared F, the voltage and frequency this particular thermal entity was operating in the previous time period. And then the static is a function of temperature and voltage. So we can calculate power using this step. The next step is we convert this power into temperature. For this, we use an elaborate model. We call this RC model. And the RC model is supposed to mimic the thermal characteristics of the die, and also the cooling solution that's available in the system, and the temperature influence of the other thermal entities on itself. So the R and C coefficients that are needed, these are characterized in our thermal lab. And this is the model that gets used in our firmware to convert a power value into a temperature. And a simple example here, if you have a step power excitation, your temperature is supposed to raise in an exponential fashion. And this particular RC model is going to give you that output. So one of the important points is that typically the firmware within the die, it doesn't have a notion of the ambient temperature. What is the external ambient temperature that you're operating in? So it sort of always assumes worst case conditions, still under the spec. So worst case could mean something like 35 degrees Celsius, which translates to about 95 degrees Fahrenheit. So this particular model is constantly assuming that you're in the worst case conditions. And then we have additional offsets which factor in I/O power and whatnot. So why do we use calculated temperature? So calculated temperature allows us to deliver robust, dependable, and repeatable performance, which is insensitive to part-to-part variations. So we can manage to provide you deterministic performance irrespective of the part-to-part for a given skew. Okay, final step is given the calculated temperature, you compare that against the temperature max temperature limit. And then if the calculated temperature is below the limit, you can actually raise the so-called P state, which is nothing but a discrete frequency and voltage combination. And then if the temperature is above the limit, you actually drop the P state. Okay, putting everything together, so there are 3 control loops here, which are similar to each other for each of the thermal entities. You have the power calculation step, temperature calculation, and then you have the decision point here. from where you actually change your P states. And the new operating frequency and voltage is sent back to the thermal entity. So for that particular interval, the thermal entity would be operating with that particular frequency and voltage. And steady state is reached when the temperature here actually hits the max temperature limit. That's how the control loop works. And it's similar on the other thermal entities as well. OK, now Richland enhancements to the AMD turbo core technology. We have added a notion of sensor temperature, which is measured sensor temperature, into the mix. So that's what this is, on-die temperature sensor readings. So using this, we indirectly detect if you have favorable thermal conditions. That is, if you're actually operating in room ambient rather than max worst case ambient, that gets reflected on the on-die real sensor temperature. So based on that, we can actually detect that, hey, I have favorable thermal conditions, I can boost more. So the way we actually boost more is we apply a scalar. So whenever we have this sensor reading indicating that we have boosting room, we actually scale this particular power, the calculated power here, we in fact actually scale it down so that this particular steps here think that I have more power headroom and more thermal headroom, and they'll actually boost more. That is, you'll be at a higher P state. That's how you get higher performance. So additional boost state has been added. Previous generation product has 2 boost states. Now we have added an additional P state there. This is on the core side of things, CPU side of things. Configurable TDP, as I've stated, allows system design flexibility, and the scaler is added right here. If you want the part to behave like a lower TDP part, what we do is we scale the power up, meaning that the control loop thinks that it has less headroom, and then it's going to settle down to a lower P state. So, and then it's going to consume lower power as well along with that. So we can mimic a lower TDP part using that mechanism. So we have another interesting feature here called intelligent boost. We try to detect if a particular thermal entity, whether it can translate the higher frequency that is being given to it, whether it can translate that to performance. There are many workload scenarios where the application code that is being run on that particular thermal entity may not be very sensitive to frequency. So it's possible that in the previous generation product, each of these control loops for operating independently, they will run towards using up all the thermal headroom, meaning they can raise their frequencies and whatnot. But it's quite possible that the raised frequency is not really resulting in performance. So you can detect those cases, and if you throttle those entities, you can give that thermal and power headroom to some other entity. So that's the concept there. OK, temperature smart AMD turbo core. So this is the feature right here. So this is where we actually use the on-die temperature sensors as well to complement whatever we were doing previously. The temperature calculation is still done. The power calculation and temperature calculation is still done. But we complement those things with these new temperature sensor readings to actually get better boost performance. So in my table here, I have the scenarios where, let's say if you are already at the worst case ambient temperature, let's say 35 C, really hot environment, maybe you're sitting outside in the sun, and then your ambient temperature is really high. So in that case, we expect the calculated temperature and the sensor temperature both to, after the control loop goes to steady state, we expect both the calculated temperature and the sensor temperature to reach max temperature limit, approximately. So there is no difference between these two values here. But in typical ambients, and because of the way that calculated temperature is being calculated here, where the temperature calculation step is always assuming worst case ambient, so if you drop your ambient temperature, it's quite possible that your sensor temperature, even after the loop reaches steady state, and by the way, I'm assuming I don't have this feature yet, right? I don't have this feature yet. So your sensor temperature would be lower than the actual calculated temperature. So we detect cases like this, and this particular feature kicks in those scenarios, and we deliver higher boost performance. And exactly where we tweak the parameters in the control loop is given right here. Okay, so whenever we have to rely on temperature sensors, you got to be very careful. You got to factor in the potential sensor errors. So the errors could be both underreporting and overreporting. I believe this is an industry-wide problem as well. But I'll briefly describe how we account for underreporting and overreporting errors that could potentially be there on these sensors. So you could have, within the same SKU, you could have, from part to part to part, the same sensor location could have a different error. It could be underreporting or overreporting. And also, within the same part, between the sensors, there could be differences in the errors as well. So through extensive characterization at AMD in our product engineering lab and thermal labs, we determined the max extent of the underreporting and overreporting errors. And then we factored those things out from the temperature margin we can leverage from we can leverage for this particular AMD temperature smart AMD turbo core feature. So two cases here quickly. So the top gray line here shows that if your ambient temperature is max spec ambient, 35C, then you can expect the die sensor temperature. This is just an example. Let's say this is our max temperature limit. You can expect after the control loop again reaches steady state, you can expect that the sensor temperature will reach 100. And just logically, if your ambient temperature is dropped to 25, and then again, you don't have this particular feature kicked in yet, temperature smart AMD turbo core, then your sensor temperature will actually drop by 10C as well. That's how the math works. So it may seem like you have 10 degrees C margin left, and you can actually leverage the entire 10 degrees C, but not quite. You can't do that. You need to factor out the errors. Especially the underreporting error is especially important, because if you don't take care of it, you can easily operate your part above the reliability temperature limits that you have. And taking care of the overreporting error actually allows us to provide deterministic higher performance whenever we detect favorable thermal conditions. Okay, configurable TDP, this is a fairly simple concept. You have a notion of rated TDP, and depending on the cooling solution of the system that you have, you can use the BIOS switch to make it operate like a lower TDP part or a higher TDP part. And this is where the scalar is added, as I've previously described. Okay, intelligent boost. I think I've covered the basic concepts already. So without intelligent boost, all these control loops, they do their own thing in terms of trying to use up the entire thermal headroom that's available, irrespective of whether the higher frequency that they're trying to grab is whether it can be converted to performance or not. So we fixed that. In Richland, we have this design where we monitor activity. So we have certain heuristics where this is especially applicable for GPU workloads, like gaming workloads. So we have heuristics where we try to detect whether the application, the piece of code that's running on the CPU, whether that is really sensitive to the frequency or not. That is, if you give higher frequency, does it really convert that to higher performance? So we have heuristics for that. And whenever we detect that the CPU is inefficiently using the power, using the frequency, higher frequency that it's getting, we apply a p-state limit. So that we apply a frequency limit. So the CPU would not be able to go above this particular frequency limit. That is, we are forcing this particular thermal entity to run cooler, so that its temperature impact on the other thermal entities would be more favorable. In this case, the GPU would have higher temperature headroom now, because its neighboring thermal entities are not that hot, and it can actually get higher temperature headroom, and it can get higher performance. Okay, a simple example here, traditional power allocation, it's possible that in steady state, you ended up with 3 watts here, 3 watts, and 2 watts at the GPU. But as it turns out, especially for GPU workloads, like gaming workloads, if you throttle your CPUs and if you provide higher power to the GPU, overall performance improves. And whenever you do this, you got to be careful in terms of the CPU power allocation. There is a sweet spot. You can't really starve the CPU too much. If you do that, you may end up in this region where your overall performance is actually lower. And same thing here. If your CPU power allocation is high, your overall performance could again drop. So there is a sweet spot there. OK, additional boost P state, I believe I've already covered it. So we have added an additional boost P state, which provides us a lot more flexibility in terms of how we efficiently hit a particular power value. OK, battery life improvements using voltage frequency optimizations and also the process tuning tweaks that we have done. The battery life has improved on Richland over the previous generation product. Special mention to the HD video playback, the efficiency has improved by as much as 51%. So AMD wireless display, the idea here is that if you have a certain thing being streamed on the display, internal display, for example, on a EDP display on a laptop, you can actually stream that same signal over to a compatible monitor wirelessly. So there are the video encoder. So this is the display controller engine here. This is the display PHY, which is driving the monitor here. But the same thing can be given to the VCE video encoder. And then this engine encodes it. Then that signal can be transferred wirelessly. So we have made additional efficiency improvements for AMD wireless display on Richland. So dock port technology, this is similar to the Thunderbolt, analogous to the Thunderbolt technology out there, but I would call it this is better because we actually transfer DisplayPort and USB 3 protocols over a single cable. And having a dock solution, you can actually drive up to 4 external monitors and several USB 3 components simultaneously. And this provides a lot more flexibility to the user. And as opposed to the Thunderbolt technology out there, these cables and everything, the solution is really cheap, really customer-centric, I would say. OK, performance numbers. As I've quoted previously, CPU performance, we have as much as 29% improvement. This is on a 19-watt TDP. The lower the power budget, we usually get higher performance improvements for the power management tricks that we play. So 19-watt TDP, we have 29% from the previous generation product. The dark red bars here are for Richland, and the light red bars for the previous generation product. PC Mark 7, which is not quite a pure CPU-centric workload, but we have sizable improvements there as well. So on the GPU side, 3D Mark 11, we have up to 41% performance improvement, and the exact system configuration. And this should be very easy to replicate as well on an OEM system. 41% improvement here, and 21% improvement on the 35-watt TDP. So the main performance main factors that drove this performance, again, let me list them again. So improvements to the AMD Turbo Core technology, which I've listed. And also due to process tweaks, we have higher frequencies for the same power budgets. And especially for the GPU workloads, we have a little bit of improvement coming from the driver as well. OK, power data. So the bars that are boxed here, these are for Richland. And as you can see from the previous generation product, the power for various workload scenarios is lower for Richland. So lower is better here. And then I have the battery life improvement here as well. Higher is better. And in general, I have half an hour to 1 hour improvements. And then special mention to this video playback scenario where we have significant improvement there. OK, in summary, greater performance and power efficiency, improved battery life, configurable TTP feature has been added, and then dock port technology has been introduced, and support added for Wi-Fi-based wireless display as well. OK, I think we should have 3 minutes for questions. Oh, OK.
2 minutes, 33 seconds. Well, thanks a lot, Praveen. I'm afraid we have time for maybe one question.
Good.
Great work. So how you said that there's a defined sweet spot. There's a range for the CPU versus GPU. So how are you aware? I mean, can you record where that range is somehow? Make them, record it somehow.
Yeah, so this is based on extensive characterization in our performance labs. So we determine what that particular range is, and it's actually inbuilt to the algorithm. So the external user can't really see it, but it's all working underneath.
Oh, so you're not doing it on the fly, but you're actually calculating it and preserving it. Is that what you're saying? You're recording it?
So the heuristic is based on a threshold value. If your activity is below that particular threshold, then the feature kicks in. That threshold value is statically fixed based on the characterization work that we have done.
Okay.
But it's working on the fly, though. If you're, yeah.
So well, my question was actually, do you know the other part of it, the high end? I can see the threshold, but it's a range, not just one number. Right?
Yeah, so this is constantly being improved on our future products. On Richland, we have a single threshold value, so it's below or above, but it's getting improved on the future products.
Yeah, go ahead. One more over here.
Okay.
And are you mic'd up?
Okay. Yeah. Josh Giff from Nvidia. I had a question about the Nvidia had a GPU coherent cache architecture. Does this also have a cache architecture and coherent cache architecture with a GPU? And does it support HSA?
It does not support full HSA, as we call it. Full HSA requires certain criteria. I would call it we are probably 60% compliant to that criteria, but we are not fully HSA compliant on this product.
And as far as having the coherent caches with the GPU?
I believe we do not have that on this product.
Thank you.
OK, well, let's all thank Praveen again. And our next talk is an interesting application of a novel technology to improving power efficiency of CPUs. A 50% lower power ARM Cortex CPU using DDC technology with body bias. The speaker is David Kidd. David has worked for 18 years on microprocessor design and digital circuit design at Intel, SciByte, Broadcom, and SuVolta. In 2010, David joined SuVolta as Senior Director of Digital Design, where he's responsible for development of SoCs, SRAMs, and customized Cs, for evaluating and demonstrating the value of SuVolta's DDC CMOS technology. He holds a master's degree in electrical engineering from the University of Michigan at Ann Arbor and has 10 patents or patents pending.
Good afternoon. So I'm going to be talking about SuVolta's DDC technology and our power shrink platform and the results we're able to achieve on an ARM Cortex M0 CPU. So the first thing I'm going to talk about is a review of the DDC transistor architecture and an overview of the power shrink platform that allows us to get the power savings that we've been claiming. I'm also going to go into the ARM Cortex M0 CPU implementation and the results we achieved. And finally, I'm going to give a preview of the kind of things that we're seeing on the 28 and 20 nanometers high-K metal gate nodes when we apply our technology. So this chart that we're looking at now is a preview of the things that I'm going to show when we go over the Cortex M0 results. We're looking at a baseline 1.2 volt implementation of the Cortex M0 CPU, a GDS identical, layout identical implementation simply manufactured on the DDC process, operates at 0.9 volts and achieves the same performance at half of the power. If we match the voltage to the baseline at 1.2 volts, we're able to achieve a 55% improvement in performance. So this is a picture of the DDC transistor architecture. It's a planar bulk CMOS transistor. That means no special tools, no special materials, no SOI, no 3D structure. However, like the other advanced technology transistors, the FD-SOI, the FinFETs that you've heard about, it does employ an undoped channel. A conventional legacy transistor uses a channel implant to set the threshold voltage. They actually implant the threshold voltage through the corners here of the gate at the source and drain. That threshold voltage implant is a major source of variability in threshold voltages and limits the amount that you can reduce VDD. The DDC transistor puts the dopants under the channel. So we can actually achieve up to a 50% improvement in threshold voltage variability. And that's on par to what you see with FinFETs and FD-SOI. It also improves channel mobility, because one of the things that hurts mobility in the channel is the dopant sitting in the silicon lattice. As the electrons move from source to drain, they collide with the dopants and they slow down. You can get up to a 30% improvement in mobility by removing the dopants. There is a highly doped layer, which is labeled number 3 on the chart. This is what we call our screening layer. It serves to stop the depletion layer from growing further. It controls the depth of it, and that is actually another way of controlling variability. This layer also controls short channel effects. And by controlling these short channel effects, it means the transistor is actually scalable from 90 nanometers all the way down to 20 and below. This allows us to have a higher effective drive current, which means superior performance at matched voltage. It means that we have a higher channel or output impedance, and we've actually previously reported an improvement of 5x in the gain of operational amplifiers on the DDC technology versus a baseline technology due to the improvement in output impedance. And finally, it enables a strong body effect. In the 65-55 node, the body effect is 2 to 3 times stronger than it is in a baseline device, and that improvement continues all the way down into 20 and 28, and that is one of the key features that we use in the power shrink technology. So our Cortex M0, we wanted to improve both the leakage power and the active power. So the leakage power is dominated by the fast corner, and what we're showing up here is a skew lots transistor measurements of leakage power versus drive current, and this is representative of a typical manufacturing variation. And you can see the slow corner transistor measurements are in green. They're less leaky and they're lower performance. In red is the fast corner. It's more leaky, higher performance. Now, if we apply a corner-specific body bias, and that would be 0 volts at slow, 300 millivolts reverse at typical, and 600 millivolts reverse at fast, we can actually pull the corners together and they overlap each other. And this is something that can't be done in a standard transistor because the body effect isn't strong enough. So this is how we want to control the leakage power. So here I'm going to talk about the idea behind the power shrink platform, which is saving both active and leakage power. This is a complicated chart, but it's essentially looking at a baseline transistor in blue and a DDC transistor in green. Okay, and we're looking at what we call the universal curve, which is how the transistor performance shifts up and down as we change the threshold voltage. We're looking at the fast, typical, and slow corners. At the same voltage, which here is 1.2 volts for a 65 nanometer technology, the DDC transistor's performance is superior to that of the baseline, meaning that the slow corner is to the left on the delay axis, it's faster. So we want to improve active power. We do that by lowering the VDD. And in the 65-55 node, we lower the VDD to 0.9 volts. That slides the DDC curve to the right, which means it's now slower. We need to recover performance, and we do that by lowering threshold voltage so that the performance is matched, the gate overdrive is matched. Now, unfortunately, leakage is exponential with threshold voltage, so you lose more in leakage than you gain in performance. This is where the body bias comes in, and we pull the fast corner down. So at matched performance, if you'll notice, the slow corners are lined up. At the fast corner, we see an improvement in leakage power because we move the corners together. This is the idea behind the power shrink platform. Now, when we apply body bias to the CPU M0, or the M0 Cortex CPU at 65 nanometers, this is what we get. We're schmooing performance on the top chart, we're schmooing leakage on the bottom chart. There is a large 350 megahertz target area that we can achieve pretty easily with body bias. And if you notice, the PMOS bias is on top and the NMOS bias is on the vertical axis. We chose this 350 megahertz target by looking at the slowest baseline M0 CPU. So this is what we wanted to target with our technology. easy to hit the performance. But if you look at the leakage increases pretty quickly as you shift the bias and you lower the threshold voltage. There's a very thin green line where we have minimal leakage power. So we need a good way to target that leakage. We've done that by developing process performance monitors. These are 55 nanometer measured results with one of our first generation process monitors. We have other ones. The idea here is we've designed them to give digital readouts so that they're easy to measure and test, they're easy to plop down into a digital system, and they measure the NMOS and PMOS corner independently so that we can actually determine what body bias to put on each device, the PMOS and the NMOS. And you can see here that the fast corner is on the bottom, the readout is lower than the typical corner, which is lower than the slow corner. In this particular case, we are using the SS zero bias as a target. And if you look at the chart on the bottom right, these are the biases that we've actually calculated from the performance monitor readouts. The fast corner is more biased than the typical, which is more biased than the slow. That's what you expect. And when we look at the results on a ring oscillator circuit, which is what we're targeting, we see the performance correction and the leakage correction. In this case, the uncorrected performance is in the left chart in the red line. The uncorrected leakage is on the right chart in the red line. When we apply the bias, we can pull in the fast corner performance to within 13% of the target, and we can pull in the fast corner leakage to TT, which is a pretty nice improvement. Now, when we add all this stuff together, we get our Cortex M0. And here we have achieved, when we look at fast corner power and slow corner delay, a 50% improvement in both active power and leakage power on this Cortex M0, comparing the 1.2 volt baseline product to the 0.9 volt DDC product. And you can see the leakage improvements in the left corner of the chart. You can also see that there is a spread between the fast corner and the slow corner for the baseline part, and that spread has almost disappeared in the DDC part because of the application of body bias. Now, we're using a 350 megahertz M0 because this was in consultation with ARM. They told us that an M0 is a lot easier to implement than an A9 or A15, and yet it's predictive of performance. In fact, the SoC that we used here is a technology evaluation platform that ARM uses and was provided to us, although we built some stuff around, we built some stuff around it. We added some SRAM, and we have some analog circuits on here. If we look at it the other way, what kind of performance can we get as we raise the voltage? I'm showing that on this chart, and we start with the same point we saw in the previous chart, which is the DDC operating at 0.9 volts, the baseline at 1.2 volts, and we're achieving half the power at match performance to the baseline. And again, the power is at fast, the performance is at slow, which is a typical ASIC design methodology. As we increase the voltage, we get to the point at 1.1 volts where we match the power. And this comes at a 35% improvement in performance. And here, power is CV squared F, so it includes both V and F. So at the same thermal envelope, at the same power envelope, you can have a 35% higher performance. As we raise the voltage to 1.2 volts, we see a 55% improvement in performance. And the DDC transistor is qualified at 1.2 volts, just like the baseline transistor. So it's got the same lifetime. Okay? This chart is a look at the implementation of the DDC transistor. The big black and purple blob is the actual output of the Synopsys IC compiler. The yellow lines are the substrate taps. We've actually routed them in columns, which is a default setting in IC compiler. Doing that allows us to route the bias network without incurring a big congestion penalty. We route 2 wires up each column, one for NMOS bias, one for PMOS bias. According to the design rules, they can be up to 60 microns apart. So in this technology, you have 300 wires between each column. We used 2 vertical routing layers. That means 600 wires. We used 4 tracks. That's because we double spaced the minimum wires. That's a routing penalty of less than 1% for implementing a bias network in this block. Turning to SRAM. I'm showing a yield chart for a production 55 nanometer SRAM. Okay, this is measured at Fujitsu. It's an 8 megabit SRAM at worst case corner at 125C, and we're showing yield on the vertical axis and supply voltage on the horizontal axis. Now, yield on an SRAM these days tends to be limited by parametric yield, which means the mismatch in the threshold voltages of the transistors causes failures in the SRAM. So you get write failures if the NMOSs mismatch with the PMOSs. You get read failures if the two NMOSs mismatch. DDC's 50% improvement in threshold voltage mismatch means that we get a substantial improvement in minimum operating voltage. In this case, we're looking at a yield criterion of 95%. The red line is the baseline SRAM, and it crosses that yield criterion at 725 millivolts. The DDC crosses at 575 millivolts. It's a 150 millivolt improvement. Now, lowering the SRAM minimum voltage allows SoC designers to lower the power supply and use voltage scaling for saving power, and it's something we actually took advantage of in our power shrink platform. Additionally, if we look at the SRAM leakage, same as the logic, we can achieve a 50% reduction in standby power in the SRAM. If we look at retention, which is a special power saving mode in SRAM where you lower the voltage to the minimum that you will still hold state, we can also achieve a 50% power savings. This, by the way, while we have a improved retention voltage for DDC, retention tends to be limited by defects, and so in that case, we use the same retention voltage for the baseline and the DDC part, and we still achieved a 50% reduction in leakage power. Now, if we use more body bias, we can actually get up to more than a 5x reduction in leakage power while still holding state. So we've been talking about the DDC silicon gate technology, polysilicon. It's applicable for nodes from 90 nanometers on down in any kind of logic circuit. Turns out it's also applicable in DRAM because their periphery, their sense amps and the like, look just like 65 nanometer transistors, so they can take advantage of the threshold voltage variation as well as the improved performance. We've also been working with foundries and IEDM on 28 and 20 nanometer high K metal gate nodes, and we're seeing similar kind of benefits. We're seeing the drive current benefits, we're seeing the leakage benefits, we're seeing the threshold voltage variation benefits. And as I mentioned, the body coefficient improvement continues, so we can also offer a power shrink option at the high K metal gate nodes. We also have another option we call design boost, which does not require body bias, but gives a substantial improvement in leakage power at the high K metal gate nodes. By the way, we do have a 55 nanometer technology in production at Fujitsu now, so it is proven, it is qualified. So the DDC technology, again, deeply depleted channel, is modular. This means that baseline transistors and DDC transistors can coexist on the same die. It's only a question of when you apply the implant masks. If you apply the implant masks first, you get DDC. If you apply them later, you get baseline. It's all a question of leaving that thin layer undoped. So for the power shrink technology we've been talking about, those are the charts here on the right. In that case, we're using body bias to get the most benefit out of active power reduction and leakage reduction, and we replace all of the thin oxide transistors. However, we do leave the I/O transistors unchanged. So the I/O driver performance doesn't change, thick oxide analog doesn't change, which is actually kind of a key benefit for customers. Thin oxide analog will change. You do get higher performance, you get higher IR out, so things do have to be tweaked. A middle option is shown in the middle, and this is the design boost option. Again, here, we don't want to use body bias, we don't want design changes. What we want to do is swap out the SRAM transistors so that we get a better VDD min, and we swap out the leaky transistors so we can trade off the DDC transistors' improved performance for leakage power. So this chart is showing the idea behind design boost. And again, we start with a chart that looks just like it did at power shrink. The DDC transistor at matched voltage has a superior performance to the baseline transistor. Here the voltage is 0.9 volts because that's appropriate to 28 and 20. And again, the DDC transistor is to the left on the delay curve, so it's faster. Now, again, taking advantage of the fact that the leakage is exponential with threshold voltage, what we're going to do is we're going to slide the DDC transistor until it lines up with the baseline transistor, and we're going to take the benefit in leakage. And when we do that, we get matched performance at 0.9 volts, and we see a substantial leakage improvement at the fast corner due to the higher threshold voltage. And again, the idea here is match performance of the baseline transistor, so it doesn't require a design change. You could actually just run the same masks, get lower leakage, and no body bias required. So when we talk to customers, leakage power is one of the main things they bring up at the high K metal gate nodes, 28 and 20. If you look at a typical foundry offering here on the right chart, foundries tend to offer multiple VT flavors. This is a representative example. We have a high VT flavor all the way up to a super low VT flavor. There tends to be an order of magnitude increase in leakage between each VT flavor. In fact, in this chart between the high VT and the super low VT, there's a 500x increase in leakage from high VT to super low VT. There is not a 500x improvement in performance. So the leakiest transistors can completely dominate the leakage power in your product. The chart on the left is divided into a low performance SoC block and a high performance SoC block, where we're looking at leakage power and we're looking at the number of devices of each type that were used in each chart. And again, we've seen data like this from customers. I've reconstructed something that's not exactly customer data, but is very representative of it. For the low performance device, which could be a modem in the SoC, we're using 95% high VT and SVT devices. The 5% LVT, I've allowed myself to fix the critical paths that always pop up, consume 50% of the power in this low performance device. If we look at higher performance devices like a CPU, here I'm using 95% SVT. I've allowed 2% super low VT, excuse me, and that consumes 70% of the leakage. And in fact, it could be worse depending on the number of low VT transistors you use. And we've seen data from customers that says it really can be worse. So enter DDC. So looking at the transistor gains that we've achieved in the 28 and 20 nanometer nodes, we can achieve almost a 50% improvement in leakage on an LVT transistor compared to the baseline by trading off the active power, the drive current versus the leakage power. We also get a small improvement in active power because the DDC transistor actually has a capacitance benefit over the baseline transistor. It's going to be less than 10%, but for leakage-dominated designs like what we've seen, it's going to have a tremendous impact on the product. So if we look at the options that are available in high K metal gate, we have a power shrink option, which is represented by the power savings bars in green. In this case, we lower the VDD just like we did in the polysilicon nodes, and we get an active power and a leakage power benefit, and that's really the best scenario. You get both benefits, but it does require design changes because you have to design for the lower VDD. You have to design for the use of body bias. If you want to keep the voltage the same, you don't want to use body bias, the black-looking bars on the left represent design boost. Here we do get some active benefit because there is a capacitance advantage, and even on the SVT devices we get some leakage benefit. But on the leakage-dominated side, we get a pretty significant, almost 50% benefit in leakage. And if you want to be, different and you want to add body bias to even the design boost, you can actually get a pretty significant improvement in leakage power because you can really collapse the leakage at the fast corner, because we're now not having to lower the threshold voltage to correct for the VDD. So you can just smash it. And these are the kind of things that we think we can do at 28 and 20. So to summarize, I've shown the results for an ARM Cortex M0 CPU where we've achieved matched performance to the baseline on a GDS layout identical design at 50% power. I've looked at the results in SRAM where we've achieved a significant improvement in VDD min and less than 50% static power and standby and retention. And we've looked at some of the things that we're going to be able to do at the 28 and 20 nanometer nodes. That's what I have in my presentation. So I'm open for questions.
Okay, we have time for several questions. Please go to the mic. Over here.
Jim McGregor from Turius Research. Real quickly, can you comment on what you've seen? Well, first off, any key customers or foundries that are using this technology today? And second, what have you seen in terms of the impact on process steps, cost, and yields in the manufacturing process?
Okay, so I can comment on a little of that, but not all of it. So we have announced partnerships with Fujitsu, and we also have an announced joint development agreement with UMC at 28 nanometers. We have other foundry partners we're working with, but I can't announce the names at this point in time. For the process that is most advanced at this point now is Fujitsu's 55 nanometer process, which is in production, and we're seeing matched yields to baseline. For costs, it is a planar technology. The only thing we're really doing is adding an epi layer, which is a blanket epi, so it's a pretty low cost. Everything else is identical. It's the same number of masks, if that's what you're asking. On some foundries, it could be mask neutral. On other foundries, it could be -1. There may be cases where it's +1. It all depends on the mixing of VTs, but for what we've seen is primarily neutral to -1 mask. Does that answer the question?
Yeah, thank you.
Okay.
Hi, I'm Robert Micklin from Ascenium, and my question is about, smaller companies being able to play with this technology, and so my question would be like, can I do a shuttle run somewhere with this technology? Can I do it through MOSIS or anything like that would be affordable for smaller companies to play with it?
Right, we don't have a foundry, so we actually work with the mainline foundries. The only foundry we have in production at this time is Fujitsu, so you can actually talk to Fujitsu and get a shuttle through there. The other foundries are not going to offer customer shuttles at this time. Okay.
But we could talk to Fujitsu, and do they have a shuttle program?
They do have a shuttle program. Fantastic. They do have a shuttle program.
Thank you.
Okay. Yes.
This is Rakshit from Nvidia. Just like how you gave the leakage and performance comparison, could you give the area comparison as well? What is your overhead? And if you could compare it with something like a picture that you showed of IC compiler, where you showed the rails for the body biasing, what is your area penalty over there?
There wasn't any area penalty for the routing. In fact, we actually did a study where we used a randomly placed substrate taps versus substrate taps in columns, and we didn't see any difference in area. And again, it's less than 1% routing consumption there, so I really don't think there's an area penalty. Now, if you want to talk about adding the body bias generation circuitry, which isn't shown here, we're estimating around a 1% area penalty for adding those. Okay.
Hi, Sotiris Bandas from Helic.
Yes.
Slightly different question on those bias lines. Could there be any crosstalk concerns potentially modulating the VD of the devices?
It does tend to be a very high capacitance node, just like VDD and VSS, and we did actually add extra spacing, but from what we saw, I don't think there's a big concern because of the high capacitance. That's my estimate.
Thank you.
Hi, Mohammad Abdullah. So my two questions.
Yes.
Is there any changes in the design rules or the automated tools that are required in the design process?
For the power shrink technology, you do need to add body bias to it. So you do have to have standard cells that are characterized for that. It's pretty simple. There's one bias per corner. It doesn't really change the number of corners. And you need to add the body bias as power rails. But for the most part, it's exactly the same flow.
Other quick question is, when do you anticipate it being available for 28 from any partner?
I can't really comment on future availability, I'm sorry. And I didn't answer your design rule question, but for DDC, it looks just like any other planar transistor. There's no extra design rules around the transistor. It's the same.
Jack from Oracle.
Yes.
So as we move into FinFET, how do you see that technology going to affect your business?
The way we look at it, and we've been told this by analysts, we see the market segmenting. So FinFETs and DDC both have their advantages, right? We both offer better variability. We both offer improved drive current. FinFETs offer more drive current, although there's a capacitance penalty for that, so you don't get quite as much speed, you get some power, but it's higher cost. DDC offers improved drive current, improved variability, but it's not much of a cost adder over the baseline technology. So we see if you really want high performance and you're willing to pay for it, you'll go the FinFET route. If you want better performance but less cost, you'll go to the DDC route. The way we look at it is it's product dependent on the technology that you want to choose. That's the way we see it. We think they can coexist in the market.
Okay, thank you.
Okay, let's thank the speaker again. Yeah, this closes this session.